Hi everyone, my name is Parnaz Nasseri. I'm a PhD candidate at the University of Toronto, and today I'm going to talk about our project on the inverse design of triple band reflective polarizing surface using a generative machine learning method. This project was done in collaboration with our colleagues from Heriot-Watt University and European Space Agency under supervision of Professor Sean Hong. On the application of these multi-band polarizers, let us look at the four-color reuse scheme that is used in multiple spot beam coverage in satellite communication. In this scheme, each color represents both downlink and uplink. However, it is associated with only one polarization, P1 and P2, where both of these polarizations are circular polarization and they are orthogonal to each other, meaning that if one of them is left-handed circular polarization, the other one is right-handed one. Conventionally, to generate the four colors of this scheme, we would need four different reflectors. However, if we can design a dual band linear polarization to circular polarization converting reflector, then we can only use two reflectors to create these four colors. However, the polarizing reflector has to convert each linear polarization to orthogonal circular polarizations in the two bands. For example, in the downlink, if the horizontally directed linear polarization is converted to LHCP, it should be converted to RHCP in the uplink. And the opposite situation should happen for the vertically aligned linear polarization. In order to achieve these simultaneous functions, it was proposed that it should be done macroscopically on the surface of the reflector. For example, you can see a metasurface-based polarizing reflector in this figure, where the structure is composed of a single layer of scatterers, and this is desirable due to the easier fabrication process. The reflector is composed of a conducting sheet in order to reflect all the waves back, a dielectric substrate, and a single layer of the scatterer. Now the scatterer is the most important factor in the design of this polarizing surface. It is judiciously designed so that it would decompose the incoming linear polarization into two orthogonal linear polarization but with different phase responses. As an instance, you can see two examples of these scatterers here. They're both asymmetric based on the coordinate system that is aligned with the features of these scatterers. Example 1 works when it is excited with a 45-degree slanted linear polarization, whereas the second example would work for horizontally and vertically aligned linear polarization. After reviewing the literature, we realized there is a scarcity of designs for triple band reflective polarizers. However, such surfaces can have unprecedented applications in simplifying antenna systems in the next generation of wireless communications. Here, we list the requirements on the electromagnetic response of the meta-atom of such surface. First, the meta-atom needs to reflect the two orthogonal linear polarizations that are aligned with the scatter features completely. Then it should introduce a phase difference between them that is an odd multiplication of pi over 2, meaning, for example, plus or minus 90 degrees, plus or minus 270 degrees, etc. Then we can define the axial ratio of the reflected CP wave in this way in dB. The sign of the axial ratio in dB only represents the handedness of the circularly polarized wave that is reflected. Ideally, we want the axial ratio to be less than 3 dB. The second requirement is the orthogonality of the reflected waves, meaning that if the axial ratio is positive and less than 3 dB in the first band, representing, for example, right-handed circular polarization, in the second band, it should be a negative value above -3 dB, corresponding to LHCP. And in the third band, again, it should go back to a positive value representing RHCP. The reverse situation is also acceptable as far as the orthogonality between the bands are maintained. The third one is that usually in wireless communications, these polarizers are spatially fed. And specifically for space applications, the typical value for the focal distance over the diameter of the reflector being more than 1, the meta-atom receives the incident field with normal incidence or oblique incidence up to and including to 30 degrees. And the axial ratio of the CP reflected wave from all of these meta-atoms should be less than 3 dB. Finally, we only want to use a single layer of scatterers for this polarizing surface to result in a low-profile reflector. Now that we know what we have to design, we propose an intelligent and systematic way that is based on a machine learning approach for the inverse design of this polarizing reflector. We employ a generator that acts like an experienced researcher and explore the design space efficiently. Compared to the conventional methods that rely on the researcher's experience and basically optimize the performance under normal incidence and live with what they get for oblique incidence, we can have a better understanding of the features of the good candidates for this polarizing reflector and optimize from the beginning for an angularly stable performance. And through the use of the generator, we can explore this design space more thoroughly. In general, there are two generative machine learning methods that can train a generator. One of them is a variational autoencoder composed of an encoder and decoder. We used this method before for the inverse design of multi-layer metasurfaces. The other one is a generative adversarial network where it is composed of a generator and a discriminator. Based on our experience, due to the demands of this project, we used a generative adversarial network because it can offer more diverse set of scatters and explore the design space more thoroughly. So we decided to go with a generative adversarial network to train the generator. This network is composed of two smaller networks, the discriminator and the generator. In the training of the GAN, these two networks are in contest with each other, meaning that the generator accepts a noise vector and creates a sample. Then the discriminator determines if this generated sample is good enough to be one of the samples in the training data. So during the training, the discriminator tries to maximize this term while the generator tries to minimize it. This term represents the cross entropy between the distribution of the generated samples and the real samples in the training data. After understanding the working principle of a GAN, we can see that the generator tries to mimic the features in the samples of the training data. Therefore, it is important that we provide the discriminator with the shape of the scatterers that are going to result in a good polarizers. How can we do that when there is a scarcity of the designs, when we don't know how to design that? In order to do that, we take a two-step curation process to prepare the training data. First, instead of randomly shaped scatterers, to expedite the search for the optimum scatter shape, we use some predefined primitives, such as Jerusalem cross and meander lines in X and Y direction. Based on our experience, these primitives offer adequate degrees of freedom to manipulate the wave the waves in the way that we want. Now, not all of these primitives are going to result in a good polarizer. Therefore, we take a second step where we define an error for the axial ratio of the reflected circularly polarized wave. As we mentioned, the axial ratio should be between 0 and 3 dB in the amplitude, and it should switch between the bands. So we can define an error for this axial ratio based on the figure, the formula you can see here. Now, we just define a threshold of 5.5 here in dB to filter out the primitives that are not good for us and keep only the ones that result in the axial ratio with minimum losses. Then we take these scatterers from the second step and their 90-degree rotated ones and include them in the training data. Some other hyperparameters that are important in the training of the GAN is that the size of this noise vector. The bigger is the size, the more diversity in the shapes we will have, but then the optimization through this space is going to be harder. So we use 50 as a dimension of this noise vector to the generator. Then some other cases, important features are the batch size is 256 when half of the batch is used from the training data, and then half of it is generated by the scatter. Then a loss function is defined for the discriminator, where the discriminator basically have to predict the probability of 1 for the scatters that are coming from the training data, and the probability of 0 for the scatters that are coming from the generated samples by the generator. Then the gradients of this loss function would be backpropagated to the discriminator and generator to update the weights of these neural networks. The Adam optimizer is used with the learning rate that you can see here and beta 1 here. After the training of the GAN is done, we can use the generator to produce new shapes of scatters. For example, you can see 8 samples here where they were created by feeding the generator by 8 50-dimensional vectors. While these features or these scatters resemble the features of the Jerusalem cross or meander line, they are uniquely shaped such that they can explore the design space for us. And that is exactly what we needed. We integrate the train generator in a particle swarm optimization through the 50-dimensional space. It means that in each iteration, for each particle, a 50-dimensional vector is fed to the generator, a new shape is created for the scatterer, and this scatterer is placed on top of a grounded substrate, and full wave simulation is run to determine if the axial ratio of the result polarizing reflector is good enough or not. We define this axial ratio error for all the normal and oblique incidence up to and including 30 degrees. That way, we can determine if the scatter is really good enough for oblique performance or not. We employed the proposed approach for the design of the triple band reflective polarizer that works for 3 different bands with 1 GHz of bandwidth centered at 9 GHz in X band, 13 GHz, and 17.5 GHz in Ku band. The axial ratio again is defined in this way, knowing that the cross-polarization reflection coefficients are close to 0. Be reminded that the sign of the axial ratio only represents the handedness of the circular polarization. After running the optimization, we can see that this set of axial ratio for normal incidence and oblique incidence in the 2 planes for theta equals 30 degree meets our requirement with the bandwidth more than what we ask for. In the first band, we achieve 1.8 GHz, where all of these axial ratio for both normal and oblique incidence are less than 3 dB, In the second band, we achieved 2.4 gigahertz. Lastly, we achieved 1.6 gigahertz in the final band. Again, we can see that the axial ratio sign switches between the bands, representing the switch between the circular polarization of the reflected wave. Now, the structure or the shape of this scatter looks like the one you can see here, where the substrate is R2 5880, and the shape of the scatter almost look like a Jerusalem cross, but it is judiciously engineered by the generator to represent this triple band axial ratio. You can see that unlike the Jerusalem cross, on this scatter we have these three dipoles connected to each other. So after the successful design, we went ahead and fabricated this polarizer and measured it. To measure the reflection coefficients of the polarizer under normal incidence, we used a quasi-optical setup, as you can see here. The quasi-optical setup is composed of two receiving and transmitting sides, as you can see here. The setup is symmetric, and it is composed of a horn and a lens in front of it, where the lens modifies the spherical wave from the horn to achieve a plane wave at the surface of the polarizer, where the phase profile is flat. Now you can see the simulation results and the measurement results are represented here. The axial ratio, you can see even in the measurement results, are below 3 dB and greatly meet the simulated results. We also converted the linear polarization to circular polarization, where again you can see a great agreement between the simulated and the measured results, and also the switch between the handedness of the circular polarized wave that is reflected. To measure the reflection coefficients under oblique incidence, we use the quasi-optical in this configuration, where again the lens modifies the radiation from the horn into a plane wave at the position of the polarizer. Now you can see again we have a great match between the axial ratio that was simulated and measured, and we can note that again, as expected and promised, the circular polarization of the reflected wave switches between the bands. To measure the reflection coefficients under oblique incidence in the other plane, we rotate the polarizer by 90 degrees. Again, you can see that the simulated and measured results match perfectly, and the circular polarization is switched between the bands. In conclusion, we showed that the proposed generative machine learning approach can be employed to thoroughly explore the design space. Different high-level constraints such as bandwidth, angular stability, and polarization orthogonality can be systematically considered in the optimization process. The proposed method yields unique polarizers where there is a scarcity of similar examples in the literature. And finally, we demonstrated the feasibility of this approach through fabrication and measurements. Thank you so much for watching this presentation.